Morning students, today we are going to discuss the combination of resistance, Kirchhoffs laws and its applications in electrical circuits. As we know, in an electrical circuit, there may be a number of resistors which are connected in series as well as in parallel. To find the effective resistance in a circuit, it is very easy if we have an equation to find their value. To help us, we are going to derive an equation for find the effective resistance when they are connected in series as well as the parallel. So first of all, we are looking to when the resistors are connected in series. Suppose we have the two resistance R1 and R2. They are connected in series to a source of EMF which have a voltage V. Since it is a series combinations, the potential difference across each resistors, it depends on the value of their resistance. At the same time, the same current is flowing through each resistor. So the total voltage in the circuit, that is capital V, equal to V1 plus V2. That is equation number 1. So from the Ohm's law, we know V is equal to I into R. Suppose these two resistors are replaced by their effective resistance Rs, then the voltage across that effective resistance is V and the current flowing through the effective resistance will be I. So by Ohm's law, V is equal to I into Rs. But already we know V1, that is the potential difference across the resistance R1, is equal to I into R1. Similarly, V2 is equal to I into R2. So using this equations 3, in equation 1, we have V1 plus V2 equal to I into R1 plus I into R2. Using equation 2, in equation 3, in equation 1, we have V is equal to I into Rs. So I into R is equal to I into R1 plus I into R2. Since I is a common term, therefore R is equal to R1 plus R2. So the effective resistance of the two resistors R1 and R2 when they are connected in series is given by the sum of their individual resistance. That is R is equal to R1 plus R2. So we can extend this result into a number of resistors. Suppose we have a n number of resistors, then the effective resistance R is equal to the sum of the individual resistance. That is R1 plus R2 plus R3 plus etc. up to plus Rn. That is R is equal to sigma I n Ra. Next we are going to see what are the effective resistance when they are connected in parallel. So we have two resistors R1 and R2. They are connected in parallel to a source of voltage V, and I is the current from the battery from the source of EMF. When it reaches the point A, it is split into two branches. So I is splits into I1, which is flowing through the resistance R1, and I2, which is going through the resistance R2. So I is the total current. So we can write I is equal to I1 plus I2. That is equation number 1. Suppose this combination is replaced by a single effective resistance, that's Rp. So we are going to replace R1 and R2 by a single resistance Rp. Then I is the current flowing through Rp and V is the voltage. Then by Ohm's law, V is equal to I into Rp. From that, P is equal to V by Rp. That's equation number 2. Since the potential difference across R1 and R2 are equal because they are the parallel combinations, the same voltage V is developed across R1 and R2. So we can express V is equal to, from the Ohm's law, V is equal to I into R1, that is equal to I into R2. So from this equation, we have I1 is equal to V by R1 and I2 is equal to V by R2. So these are equation 3. So substitute equation 2 and 3 in equation 1. We have I is equal to, from equation 2, I is equal to V by Rp. So I is equal to V by Rp equal to, using equation 3, I1 is equal to V by R1. So I1 is equal to V by R1 plus I2. I2 is equal to V by R2. Here V is a common term. So 1 by Rp equal to 1 by R1 plus 1 by R2. Or Rp is equal to R1 R2 cross multiplying and taking the reciprocal. So R1 R2 divided by R1 plus R2. So this is the effective resistance when the two resistors R1 and R2 are connected in parallel. If we have a more than two resistance, then 1 by Rp is equal to 1 by R1 plus 1 by R2 plus 1 by R3 plus etc. 1 by Rn. That is the reciprocal of the effective resistance in a parallel combination is equal to the sum of the reciprocals of individual resistance. Okay. So you can see that when the two resistors are connected in series, we have effective resistance equal to the sum of the individual resistance. So the effective resistance will become greater than the largest value of resistance in series combination. But at the same time, in parallel combination, we can see that the effective resistance will be less than the lowest value of resistance in the parallel combinations. Suppose we have a two resistance, 2 and 3 ohm. When they are connected in parallel, what is the effective value of resistance? You may calculate. Rp is equal to 2 into 3 divided by 2 plus 3. That is 6 by 5. That is Rp is equal to 6 by 5. So you can see that this 6 by 5 is values lower than the lowest value in the combination. That is, it is less than the 2 ohm. Okay. So by connecting the resistors in parallel, the effective resistance will decrease, and when they are connected in series, their value will become increases. Suppose we have the two resistors. One is the larger resistance, capital R, and small r is the very small resistance, which is connected parallel to the capital R. And I is the current which is entering the junction A split into two. The current through capital R is taken as I capital R and the current through small r is taken as I small r. Okay. So we can write I is equal to IR plus I capital R plus I small r. And from that we can write I small r is equal to I minus I capital R. Since it is a parallel combinations, the potential drops across capital R and small r are the same. So from the Ohm's law, we can write the potential drop across each resistance. That is I into I capital R into capital R equal to, that is the potential drop across capital R equal to the potential drop across small r, that is I small r into small r. So we can use the expression 1 in this equation. I capital R into capital R equal to, instead of I small r, we can use equation 1, that is I minus I capital R into R. Just expand it. I into small r minus I capital R into small r. The next step, I capital R into, we are taking the second term into in the left side. So I capital R, IR into capital R plus IR into small r. So we can combine IR into R plus capital R plus small r equal to I into small r. So from that, I capital R is equal to I into small r divided by R plus small r. Similarly, we can derive the expression for I small r, that is I small r is equal to I into capital R divided by R plus R. That means when we look into the equation 2, suppose we think that small r was not connected, then capital I is the current. The total current I will flow through the capital R, that is the larger resistance. So when we connected the smaller resistance R, small means suppose R is the 99 ohm, small r may be a 1 ohm. Okay. So when we connect small r, what happened? The current through the capital R, that is I capital R equal to, from the equation 2 we can see that I into small r divided by R plus R. That means initially the whole current, the total current I is flowing through it, but when we connect a smaller resistance parallel to it, the I capital R becomes I into total current into small r divided by R plus R. That means only a very small fraction of the current will flow through the I capital R. The remaining or the majority of the current will flow through the small resistance small r. That means when we connect the small resistance parallel to a larger resistance, it will bypass the majority of the current. So in electrical circuit, such a resistance connected parallel to the larger resistance is called shunt resistance. That is the principle of shunt resistance. And also from the equation 2 and 3, we can see that, so when there is a current, when it is split into two branches, then current in the one branch, I capital R or I small r. So we have the expression. When we look into equation 2 and 3, we can see that they have the similar expressions. So the current through the capital R equal to main current into total current into the resistance in the other branch divided by sum of resistance. Similarly, the current through the smaller resistance I small r equal to again main current into the resistance in the other branch divided by sum of the resistance. So we have a general expression for the current in one branch, that is equal to main current into resistance of other branch divided by sum of both resistance. Next we have the two laws, that is known as the Kirchhoffs Rows. So to make the electrical analysis simple, these laws help us to calculate the current in a circuit or the potential drop in a circuit, etc. Here the Kirchhoff's first law, it states about when a number of currents meeting at a junction. Here we call it as an electrical junction. Here the sum of the currents are coming and the sum of the currents are leaving. So Kirchhoff's law for this first law states that the algebraic sum of the currents meeting at a point is 0. That is, from the figure we can see that I1, I2, I1, I3 and I5, they are the incoming currents. That is we take as positive. And I2 and I4, they are the outgoing currents. They are taken as negative. So algebraic sum of the currents, that is I1 plus I3 plus I5 minus I2 minus I4 equal to 0. The algebraic sum of the currents meeting at a point is equal to 0. That is sigma I equal to 0. That is the sum of the currents entering equal to the sum of the currents leaving that junction. That is the Kirchhoff's first law. It is also called junction rule. Next is the loop rule. So it deals with some electrical loops. So from this figure you can see an electrical circuit. So when we talk about the loop, that is from in this figure we can see A, B, D, A. This is an electrical loop. And also B, C, D, B. That is also an electrical loop. And we have one more loop, that is A, B, C, D, A. This is another loop. So the second law states about an electrical loop. So in an electrical loop, there may be a number of electrical components. There may be resistors. There may be a source of EMF. So it talks about the EMFs and the current and the resistance. So the statement is that in any closed circuit, algebraic sum of the products of current and resistance of each part of the circuit is equal to the total EMF in that circuit. Algebraic sum of the products of current and resistance, that is I into R, the products of current and resistance. The algebraic sum of the products of current and resistance, that is sigma I into R equal to the total EMF in that circuit, that is sigma E. So we can look into the first loop A, B, D, A. So when we take the algebraic sum, we have to specify the positive and negative directions. Here, the positive value of the products of current and resistance, that is positive value of IR, is taken when traversed in the direction of current. So if we take the direction here, that is anti-clockwise. Then I into R, I1 into R1, that may be taken as positive. Okay. So in the case of the cell source of EMF, when we traverse from negative terminal to the positive terminal, the negative electrode into positive electrode through the cell is taken as the positive value. So when we look into the loop ABDA, we are going to apply the Kirchhoffs second law, the algebraic sum of the products of current and resistance, that is I1 into R1. So in this case, we are taking this is the anti-clockwise direction taken as the positive. So I1 is the current that is flowing in the anti-clockwise direction. So I1 into R1 can be taken as positive. So I1 into R1 plus, here also this is our direction, anti-clockwise. I2 is also flowing in that direction. So I2 into R2 can be taken as positive. I2 into R2 plus I3 is also flowing in our anti-clockwise direction. So plus I3 into R3 equal to the source of EMF, the total EMF. Here we have only one cell, and this is our anti-clockwise is our direction. So when we look into the negative terminal to positive terminal, so that is also in the direction of current, so we can diagnose this is positive. So for the loop BCDB, okay. So I4 into R4. Again, we are taking this as the anti-clockwise direction is the positive. So I4 into R4 is the positive plus I5 into R5 is again a positive. Then I2 into R2. So that is the opposite direction. So we have taken this is our direction, anti-clockwise. I2 is flowing in the opposite direction. So negative I2 into R2 equal to, there is no source of EMF. So that is total EMF equal to 0. Second, we can apply the second law. Second law is also called the loop rule because it is deals with the electrical loops. So it is also called a loop rule. So when we apply the loop rule through in the that is A, B, C, D, A, we can have, again we are taking this is anti-clockwise direction is taken as positive. So I1 into R1 is a positive plus I4 R4 plus I5 into R5 plus I3 into R3 equal to E. Here we have only one cell. So that is the Kirchhoffs laws. It helps us to analyze the complex circuits in a circuit.